2.3. We would now like to make taking limits more efficient. So the first thing we're going to do is develop some limit laws. Limits. Laws. They're all written in the textbook. And they'll provide us a backbone for calculating limits without having to use the definition directly. The definition of limit is very cumbrous, and this will lead to a lot of leniencies in calculating limits, and we will not need to resort to the definition at all for the rest of the course. So some very basic ones are that the limit as x approaches a of the function x is a, and that's pretty obvious, because if x is approaching a, then what else is x approaching but a? And you have the limit as x approaches a of some constant function, right? It's always the same value, is that same value. It's also pretty believable without any proof, because since it's a constant, the fact that the independent variable x is approaching some number really doesn't impact the value here at all, because it's never changing, being a constant, so therefore its limit is also that self-same constant. Right. And now there's some limit laws that appear to be something like distribution laws for the limit symbol. If you think of the limit expression here, limit as x approaches a, as being an operation on functions, perhaps. So we'll say if the limit as x approaches a of f of x and the limit as x approaches a of g of x exist, then some things hold true. And all this would be proven out using the definition very strictly, but we're not interested in that right now. Just want to get to these efficient modes of taking limits. So let's see, if that is true, then a bunch of limit laws are true, and that is that the limit of f of x plus g of x as x approaches a, right? The limit of the sum of these two functions will be the same as the sum of the limits. Again, it will appear like a sort of distribution property for the limit symbol, right? When the symbol is kind of like being distributed to each of these two functions in a way. And that's a reasonable way to think about it. Okay? Again, it's only if these two separately exist already, as it says here up in the if part of this statement. Right? These two have to exist separately that this distribution should have any validity. Okay? And you keep going, it would be the same as if it were a subtract here, really no difference. Okay, so we just put that there. It's fine either way, whether it's a plus or a minus. Same basic property works for products. If we had the product of f and g, we took the limit, then that would be the same as the product of the two limits. Again, it looks like distribution. Only I'm not distributing over a sum or a difference. I'm applying the limit symbol to both of the factors in this product in here. So too for division. There's a very special exception for division, one to watch out for, and it will come up constantly. The quotient of two functions will be the same as the quotient of the limits. Again, looking like distribution. That looks so sharp there. one exception. As long as the bottom limit, even if it should exist, right? In this particular scenario, we could not let the bottom limit for g be 0. That would not be allowed. So that cannot equal 0. Okay. There's a couple more very basic ones. I'll just include them here. Limit of f of x raised to some power. It's like the limit symbol will move inside of the exponent and apply itself to f, with the exponent being applied after the fact. And one more, same thing as an exponent is a root. So we'll have the limit as x approaches a of the nth root of f of x. And again, the limit symbol will be able to slide inside here. And you can take the root after the fact. Now, again, that's as long as the original limit exists for f of x, as stated at the beginning.